All right. Okay. All right, so as you can see on the screen here, you're getting your first from our class, your first table of table contents, periodic table. Okay. So you get this one. I'm holding it upside down because this is the periodic table of mistakes. Periodic table of mistakes. I'm going to give you a certain amount of time to see how many mistakes you can find on this. How many mistakes you can find on this, right? Do it yourself as quickly as you can. Maybe there's a prize for the winner. I don't know. Okay. Periodic table of mistakes. Find them, circle it, see how many you can find. Yeah, you would know that study hall. And then the last study hall is like Coco, why are there 3 kids in your study? Periodic table of mistakes. Are there 3 kids in your study hall?
Yes, including me and Dr. Lon.
There are 37 kids in our study. There are no kids. We had some dogs in our study. That's why it feels so loud. Okay, medium. Okay, this is mistakes. 2 is on. Okay, go. Circle of mistakes that you can find. You can refer to up there. OMG is not on. Oh my God. The magnesium is not. How many can you find? Selenium is not 14. Maybe 3. So that's I don't know. And that is not. Kelly, all cap. Not
That's how.
iron is not.
I know, did you just say I will go?
Iron is not manganese.
Yeah, you said I will.
Iron, okay, 8 and not. That's poison. Oh, I have the silicon, yeah, silicon, selenium. Yttrium should be no, krypton. No, but it's not. It's coming down. Oh, okay, you could be on there. Exactly. Stop yelling. Stop yelling. And then it. Okay, 42 is not holy. Oh my God, no, that's more working on things. Gold is 18, not 18. Right, it's not even, this is silver, but it should be silver. It's probably atomic mass. Wait, the atomic mass, I don't want to pay attention. Oh. Yeah. Okay. How we doing? Okay, so are we finding?
A US hospital. It's, there should be. Yeah, they switched it.
When you think you found, them all, raise your hand.
Bismuth, is that
Okay, it's 3 minutes.
this will be it.
3 minutes to find any mistakes that are on this periodic table of mistakes.
What is that? That should be. Half names are on. Laurasium is there?
I didn't see that.
How about the element of surprise?
What the? Like in the 100, just becomes like the element has like range. It should be. Yo, it's a dog food for like moving along. Yeah, Mike. Oh, yeah. Yeah. And studio.
Okay, raise your hand if you think you have them all, and I'll write that.
There's, okay, hold on, if you
I know.
switch two elements, like if you switch helium and hydrogen, that's your mistake. Like, oh. There's the wrong way. What are you doing?
Okay, Eden says 17.
I have 1, 2, 3, 7.
Who else?
I have
That's great.
Hold on, 8.
720.
Oh, also this. That's, they're just thinking of another thing. Yeah, no. It should be through phone. You as well. Yeah, it should be through. Why did you? Huh?
You.
It should be. I just.
Yeah.
That's not.
What do you do? I shower every day. What do you do?
Let's count up. Now we have a minute. Who wants to tell me, what how many you have?
Hold on.
Okay. Time's up. Who wants to tell you how many you got? Huh? Eric, how many you have?
I can get 20 pounds out of you.
Huh? Count. Count. What do you got? 22. All right.
Oh, this. Well, I found 21.
Come on,
And mine, because it says flat 2. Flat 2 in the.
Where's that?
7. Flat 2. Flat 2. I didn't look for spelling errors. Bro, why are you not questioning liver boarding?
I don't see it.
What's the key? What the hell would you look at 160 for? I'm looking at like 19. Well, because like going on from I would, if I already went from like, the one. I don't. Exactly. That's what I'm saying. So why are you fucking standing and not covering? Because I don't know if that meeting is actually.
Okay, anybody else have?
I can make it.
Okay,
Standing.
that's it? No more, okay. All right, so now. It looks like Sunny has, and I checked, Sunny has the most. Very good. So
Oh, it's open, it's open.
Sunny has the most. Sunny's gonna start. Sunny, come up and circle one that's wrong.
No.
And Sunny gets the trophy,
Yeah.
a thumbs up trophy. for that.
Oh.
There's one in the thing, winner. Okay, let's see, collectively, let's see how many, she had 22.
What's it last?
Let's number one. Okay, you're in the wrong place. Come on up, Jeff. All right, one at a time, let's go come up here and you probably should go around twice to get all of them. Okay, how you in the wrong place? 18. Oh my God, OMG, okay. It's getting a little dramatic there. Okay, Florian is not FL, it's not, that's Florida, it's right there. Okay, so that's that. Yes, come on, Benjamin, you flat eyes. Checking your eyesight too, yeah.
What's the name of the other? Well, what is MC?
MN is not, MN is what?
MC is one. One fifty, don't tell me what it is. What is MC? Spin it out. It's in like the bottom, right? Like towards the bottom, right? You count back.
Okay, so it's circle two and two positions have switched. Manganese is not magnesium, right?
What is it there? What's the other name?
Come on, next, phone, come on.
You got it. You. Yeah, he's right. He's right, yeah. It's not good.
Come on.
Okay, I guess.
Bench code here, it's not,
Oh,
JK, you don't like that? Oh, it was someone's initial. Okay, potassium. Potassium is a strange one, it's K, right? Okay, Devin, come on. Come on, let's get this fast moving. See how many we got?
I literally recall.
That is true.
You literally not
Get ready, get ready.
You were literally
Go, get ready. That is true. Am I wrong? Okay. Oh. Yeah. Am I wrong? It's by heart. He knows the song.
What a terrible.
No, I just know the first three of two.
That's pretty good. The first 20 we know. Okay.
That's so bad.
But
Oh, there it is.
You're cutting in front of him.
Okay. How are you?
Come on, come on. Come on, you take this step off.
I thought I was after something.
But you were faster than that. Okay. Maloney.
Oh, it comes on me.
And looking most good. Sorry.
No, I'm what, I call it one.
Yeah.
The mom. That was your time. Should I do I usually say.
Okay, let's start again. Sonny, come on up and do another. Oh, wait, 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 you got it.
Yeah, and then he's like.
Come on, let's get moving here.
Even that.
Yeah.
Good God.
Here. Great. Actium. So that Actium is not AACT, but that's the American Association of Chemistry Teachers. I'm a member of. Oh, tungsten. What then do we give tungsten? Okay, Sonny. What is tungsten symbol? W. Okay, that's a strange one. Let's go, keep going. We should make it around again. Okay, silver is in the wrong place. Silver and gold is switch, right? Silver should be AG and gold should be AU. Here. Oh. We're leaving the caps off because sometimes they're hard to get off. Okay, gold and silver switch. All right, see if we can make it around. We should be able to make it fully around again to get 24. Little hint there. Okay, uridium. It's just Y. Okay. Come on, Desmond. Be ready to come up. Yeah, we're gonna go again. It may be getting now to the ones that are harder to find. Okay, it's giving an explanation here. Cesium, okay. What's the matter? It's spelled wrong? Yeah. It's spelled CE. It's only Cesium. Oh. CAESIUM. Oh, that's right. Okay, come on, where are we? Bowen, come on. Wait, can it be intertwined? What's wrong with Cesium? It can be intertwined. All right, that's not right.
The spelling can be interchangeable. I said so. Should I erase this?
My bad. Huh?
Ours.
Cesium disqualified. Yeah.
They,
Okay,
I'll do one for Benjamin.
okay, go. Oh, thank you.
It says leave you.
PU, why wouldn't it be Steve?
Because it's.
Oh, here, there. Thank you. Okay, clever. Okay. Then, come on. Can we go around again? We should be able to. You like plutonium?
Yes, no, I like stadium.
Plutonium, oh. Right, you know, everything.
Wait, I'll do one for Ben.
After 92.
I didn't draw and.
That trench coat came from where?
Where's the spell?
You didn't pour on your blue trench coat?
Looks like a,
Oh, fun.
looks like a detective, doesn't it?
Wait, let me do one for Benjamin.
No, let me do it.
No, Ben.
Come on, Clyde, let's keep going. Sanju, come on up.
Hold on, let me hold on.
Go on.
Oh,
Alright, hop on.
what happened? That's in the wrong way?
Yeah, that's good.
Oh, Xenon and Krypton. Krypton. Okay, that sounds like, Superman. Superman is in the building. Okay, where are we? Yes, come on, we're gonna see if we can get it twice around. That would be 24.
I don't know. I don't know. Oh.
That's
Well, it is the call.
What else do we have? It should be two more. What are we missing?
That's what I'm saying.
Why are you adding the?
I don't know, thirty.
We got four other things before the meeting.
Yeah.
All right, who has another one that we don't have in here?
Isn't that like equate? No. Like, is this how, like, this equation? Yeah, it's really not that, it's that, right? Yes, but that.
Okay, what do you got? Huh?
Circle down. If I have.
Yeah, okay. This one has
Yeah,
reverse.
yeah. They already know.
Okay, all right. What else?
And then you know, square root is.
No.
Okay, okay. So it's got the whole, thank you, Kevin. There's, okay.
A square.
Okay, so if you're looking really, really close, this one is really, I didn't expect. This one, these two molar masses are reversed.
No.
Okay,
No, no.
all right, there's 25 of them. Okay, all right, good job. So what did we get out of this? Insanity. Okay, but we gotta look, we look a little closer at this wonderful document that we're gonna be using. We're gonna use it a lot, right? And good job. You look closely, inspected it. We had a little race there. Sonny came in first, got a grand prize of gold thumbs up. Okay, so I'm gonna give you all one of these as a souvenir of how you did very well with these champions of the atomic theory, right? Brought us to the point of over here. Irwin, our friend Irwin, who he was a scientist, a statistician, Schrodinger, who developed this idea of probability of finding electron in a given area. What? Schrodinger's kind of. Oh, yeah, okay. We look at that kind of function too. Okay, now, okay, for today. Okay, let's close our laptop, please. We're gonna do them right now. Okay, we're gonna do a final review of this atomic mass, atomic number, the difference among elements, right? What makes an element different from another, and then introduce the periodic table. Some of the things that we need to know about how to use the periodic table and some of its structure. All right, we started out with this matter. We know matter generally is either mixture or pure. Pure substances are either what? They are either a compound, or we call a molecule also, or an element. What about the mixtures? Very good. Homogeneous and heterogeneous. Okay.
Yeah, good job. The solution.
Okay, an element, we know an element, these are the building blocks. An element, you could be as synonymous if you're in biology, you could think of You can think of amino acids, you can think of cells, building blocks and stuff, right? There are, right now, there's 118, but some of them are artificially made. But 90, 91, 92, 92, we stop at uranium, which are the ones that are found in nature. So that's, over here. Everything after that is in stencil, and it's kind of identified, these are all the imitation ones made in laboratories by throwing atoms at high speeds, atoms or particles at time, and seeing if things can hold together. It might be for a millisecond, it might be a couple of seconds, but they enough for the scientists to characterize it as a new thing. Smallest piece, we call that the smallest piece. We know that there's isotopes. There's different varieties of a given element, like there's different variations. And for instance, carbon has 4 isotopes, hydrogen has 3, etc. Iron has a whole load of them, and they vary in the number of neutrons. In their neutral state, they have the same number of protons and electrons. And then again, here's the relative masses. So we consider the proton and neutron to have 1. You don't have to worry about out here. And then the electron so much less that we don't consider its mass because it's relatively 1,800 times less than a neutron or a proton. Okay, we're gonna do a little activity with this. This is a really cool depiction of our periodic table. It's called ptable.com, really easy to get to. It's a great reference tool, and we're using it in a little exercise today. Okay, so we did a little practice with this. You did it for lab, and that's to get a weighted average. If we know what element we're talking about, and we know the isotopes in nature, and we know the distribution of them. For instance, for this one, 2 isotopes, and one we're told has a mass number or atomic mass of 151, and the other 153. This one in nature is 48%, 48.03%. This one 51.97%. This is how we do the weighted average, right? So we make the percentages distribution into decimal form, multiply them and add them. And in this case, it's kind of roughly almost half and half. So it's going to be somewhere between the two. And it is, it's right between them. It comes out to 52. Okay. Any questions on how to figure that out? And that's why all of the atomic masses that we see up there, they all have decimal places, maybe out to the 10th or even out to the 10,000th place. Okay. All right, so atomic particles. This is a simplistic cartoon of it. The way we see this in cartoons. Well, it's a good way to think about it. It's actually not as perfect as that. In the nucleus. Okay, so again, just to review, protons are positive, so that makes the nucleus positive because the other things in the nucleus are the neutrons, and you probably know there's other subatomic particles, things like gluons and quarks and maybe 1 or 2 other ones that they're still exploring, still understanding. By the way, right down the road, Princeton Plasma Physics Laboratory, Princeton University, does top notch. They're one of the world's leaders in trying to understand this, also into trying to get fusion to work as an alternative energy. So really cool place. And we're going to continue to try to get a visit over there. Would be very cool. Okay. And then we had different models of how this might look from pudding, and we wind up with the Bohr model we'll be using. Okay. Protons, they tell us the atomic number. With the periodic table, they tell us the element, what it is. And we assume that it has one atomic mass unit. When you see AMU, that's what it stands for, atomic mass unit. Electrons, you'll know that electrons, even though we consider them, they not have significant mass, they really are, as we go further, almost the most important part of an atom. Because that's why things react, that's why things bond, the electrons. And that negative charge. Now, when we start to think about what does an atom look like, we begin to at least think about it in these what's called energy shells or energy levels. And that's where the electrons kind of stay. That's where their cloud stays. And for the Bohr model will be actually just make a circle here, and we'll be drawing these circles around here, and then putting the electrons where they will be, or where we think they're going to be. And there's a certain way that we populate the energy levels. Okay, each energy level that we're going to see, this is the Bohr model, could contain a certain number, and only a certain number under normal circumstances of electrons. The first energy level, you can already see when it's just showing carbon and oxygen, has 2. The second energy level can have up to 8, and then we'll talk about how that expands. There's a little formula that we can figure out how many electrons could be in an energy level. And what? Huh? So it's actually a pretty simple calculation when we say what's the most that electrons that we could expect under normal conditions in where this is the energy level. And it holds true to a certain point, but for our initial discussions, this holds true. If this is N, how many electrons would that be? This is N, is the energy level. So the first energy level contains how many? 2. Yeah, that's what we see. Okay, if it's a second energy level, 8. Huh?
2 plus 6.
Yeah, we're adding them together. That's right. And then when we're at the third energy level, if this is 3, okay, we'll explore this as we see it. We're going to getting a little ahead of ourselves. Okay, that's the way we'll estimate. So for now, just know that we have first energy level, second energy level. For now, it's okay. It grows, but we'll talk more about this. Neutrons, they're compatible. They're about the same size and mass, but they have a different charge. And we talked about this signature, the signature of hydrogen. That's the simplest element that we know. Mass number and atomic number. And from these numbers, you can tell how many neutrons it has. So how many, if this isotope hydrogen, how many neutrons does it have? None. It has none. It's neutronless. Neutronless. Everybody see that? Okay, an atom, as we see it, unless we're told differently, we assume that it's neutral, so the protons equal to electrons.
Did you consider like performance in that?
What?
Oh wait, no. Wait,
Mass is neutrons plus electrons.
Yeah,
So don't you also use?
no, photons plus neutrons.
Oh, right, right.
Okay, so here are two other isotopes of hydrogen. Two other isotopes of hydrogen. This one has one neutron, this one has two. So if we were to write the signature of this, we would do this. H, it's still one here, but it is what up here, two. And this one is three up here and one. Okay, everybody see that? That's how we write those signatures of those two isotopes of the simplest element we know, that is hydrogen. And it turns out that this one here is radioactive. Radioactive because it is kind of it's very busy, it's very congested inside its nucleus, and it wants to give off energy. So with time, it gives off energy and things change in here. Gives off energy, and that's the radioactivity that's given off. Okay. And so that's an exciting unit when we get to that, when we talk about radioactivity. Okay, here's some more examples. Helium. So helium has several isotopes like this. Carbon, the carbon one. These are two isotopes of carbons. This one is interesting because carbon 14 is also radioactive. Right, it has two extra neutrons compared to the most abundant. Okay. So then some examples, right? So we can simplify the signature a bit and just put it like this, right? Because why? Why do you think we can just simplify and write the signature like this? Why can we simplify the signature without and leave out this thing? Leave out the bottom number. Why can we simplify? Yeah. Right, yeah, because it's obvious that this is gonna be one. And it's obvious this is gonna be two. And it's obviously this is gonna be three. But that's the atomic number, yeah.
Why don't we write it at the first place?
It's extra. Yeah, it's extra, it's just identifying it. It's telling us the number of protons if we don't happen to have a periodic table.
Right.
Okay,
Yeah, Devin.
Devin, no,
I'm sure Devin will know about
Devin told us the first day, he got that down.
No, I did not say that.
Who knows the song? We'll hear the song. Okay, this is the next fun thing we're gonna learn. We're gonna learn how to put these dots, these are called electron dot diagrams, in which we put the important electrons for each element. And they call the valence electrons, so we'll learn about that very shortly. Periodic table, okay, some very important stuff about the periodic table. It's first kind of organization. We're gonna learn about what's a period, what's a group. And then where are the categories of types of elements on the periodic table? Okay. So let's go into that. Location of metals, non-metals, and metalloids. Everybody hear of metalloids? That would be the one that some people have heard of them, metalloids. And also their phases of matter we could tell with a prediction in the periodic table. Okay, who's this? This Dmitry Ivanovich Mendeleev. So where do you think he's from?
biology.
Sorry? Russia, he's a Russian chemist. He he thought a lot about this, made a lot of observations. A lot of chemistry was being done at the time in Russia. And so he was in touch with a lot of the scientists making these early discoveries. Finding this stuff, isolating things and saying this looks like a different kind of material. And characterizing them as elements. When he thought about how do we organize these, there were only about 40 elements known. 40 elements known, and he tried to think of how we should be organizing these so we can go further with them. How do we understand this stuff? Like making a graphic organizer, functioning. As you're learning things, how do you explore things, even when you get into your research? It's very important to diagram things, to draw things, put them so you can think about them, categorize things, because that's kind of the creative process. And that's what he did. And the story is he had these dreams a lot about the elements and how to organize them. And
dreams about elements.
absolutely, yeah. You dream about things that you're exposed to and thinking about consciously, and lots of times we don't recall our dreams. Anyway, recall a recent dream?
I recall I had a romantic relationship with one of my dreams.
That's all.
Which is why that's a dream.
Okay, Merrick did that dream. About running and finishing and running a marathon, maybe, no?
One of my cousins died, and I cried like very.
Yeah.
Who was it?
Well, it was like classic from.
Oh, sometimes dreams are. Hey. Sometimes dreams are very quirky that it almost seems like we're tapping into something that, you know, it's kind of strange that may happen, or we're putting together something. Maybe, sometimes it's just our imagination running wild and exploring things, or it's maybe things that we're concerned or worried about. Things like climate change, or whether I'll ever have a girlfriend or a boyfriend. Yeah. You have a boyfriend? Yeah. And you know what, and studies have shown this, and I know this happens to me. It's really when you have a full night's, whatever full night's sleep means to you, like 7 hours or even 8 hours, then you have enough time to kind of complete these cycles, and then it's more likely that you remember things. So, okay, a little diversion there, but he thought of how to group these, and eventually it came down to this, and as elements filled in, it really made a lot of sense. Okay, pay attention now, it's very important. As we go across, these are, you might think they're rows. They are rows, but we call these periods. Period. So what does a period mean? In terms of the periodic table, what do you think that means? We go across here, and then it's like the next one.
Series.
Okay, it's kind of a series for the next one. It's very different. It's not logical to go this way. It's more like these, and then go across again. And there's a pattern to them. It happens periodically. And if you look at the mass is what we look at it, we kind of thought about trends. Masses definitely increase as we go further. It turned out the number of protons. But there was a definite reason to say, okay, these have this characteristic. The next one, 37 turns out it was more like these alkali metals. Okay, And then it turns out up and down are called groups. Okay, periods go across. And groups go up and down. Anybody have something, how are you gonna remember that? How about this? You write a sentence, you go across and you put a period at the end.
Oh, that's smart.
Okay, periods go across, horizontal. And groups and families go up and down. Okay, just a quick characterization and see how these groups are alike. Now it's in the textbook, and I'm gonna give you, I'm gonna post something also kind of that have this information on them. So it turns out that this first group is group 1, but it's also 1A. Next time, I'll give you a real periodic table, not just one of the mistakes that you can start making notes on for remembering things. All right, it turns out that all these here are soft metals at room temperature. They're very reactive. Only one valence electron. So this is group 1, one valence electron. It turns out that for many groups, at least 8 of them, that the number of groups tells us how many valence electrons. These are the outside electrons, the ones that are reactive, the ones that we're most they're most important to us, really. Okay, so those are and they have these characteristics. If you put these into water, they violently react. They violently react. They interact with water tremendously fast, producing hydrogen gas. And as we go down here, they become more reactive.
Sodium is not explode.
It,
It just dissolves.
well, it does kind of give off a lot of energy, and we'll see the difference. Okay, alkaline earth metals is group 2. They have 2 valence electrons. They are also reactive. They're so reactive, we don't find them alone in nature. They're already bonded. They found their boyfriend or girlfriend, and we don't find them alone. Transition metals are these this big square in the middle. Big square in the middle. These are called transition metals. Transition metals from 3 to 11. Okay, with 18 groups going across. Metalloids. So metalloids are these in between the metals, and then we get into the non-metals. So some of these are on, we call this like a staircase. They have characteristics of metals, and then again, they have some characteristics of non-metals. Halogens are 17 of 18. And we also number these by, and I'm going to show the whole periodic table again. This is that also 7A. It's 17, there's also 7A. So these A groups are ones that we can predict much better. We'll talk more about that. And finally, the noble gases. Just a quick. We can predict with better accuracy how many valence, how many reactive electrons they have. These are the noble gases. They have 8 valence electrons. They don't interact with each other, with anybody. Except for exception of xenon that can interact. Okay, and then there's these others, very large, much larger ones. They seem to have also common characteristics. We don't talk much about that. Okay, isotopes. Talk about isotopes. Here's another interesting feature you'll come across. Here, this is carbon. All these are carbon. So when an element on its own, it does have if it's on its own, bonded to itself, like carbon is lots of times. And if it forms physically different materials, then these are called allotrophs. Or allotrophs. Look at how versatile carbon is. it makes up a big part of us. It's the living, all life that we know of is based on carbon. Diamond has a certain way that the carbon bond. Graphite are these sheets. Buckminster Fuller. This is an interesting molecule of 60 carbons that form this kind of thing. And named after an architect that made these dome figures. And finally, nanotubes. So nanotechnology based on a lot of what synthesis chemists can do with carbon, making interesting structures. Okay, we mentioned these diatomics. Most elements don't exist on their own. There are some, like we just mentioned, the noble gases. And then some exist like this as diatomics. There's 7 of them. There's 7 of them, and we could remember them because this guy, Professor Brinkelhoff. Professor Brinkelhoff, and he's from diatomics. Brinkelhoff. So if you pull this apart, all 7 of them are in here. There's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Right? So you should know these diatomics. Okay, there's 7 of them. Okay. Metals in the last thing, and then we have an activity I'll give you. Metals lose electrons. Metals lose electrons. That's one characteristic very important about metals. Non-metals in general either gain electrons or share them. Right? We'll talk a lot more about bonding, but just to mention that now. So where are these on the periodic table? Periodic table also predicts where these are. Okay, about 2/3 of the table, a little more than 2/3 are metals. And then up here are the non-metals. All right, many of the non-metals are gases. You look at these, there's noble gases, there's these are over here are the these are the diatomics, this little 7 over here, which is another way to remember them. You have a periodic table and you see this little 7 there. Those are the 7 diatomics. We have 1 over here though, hydrogen. There's 6 here and 1 over here. The diatomics. Now, if you look here, we'll talk more about this, but look over here. I said that there's 8. These are representative or the main groups that we can predict. 1, 2, 3, 4, 5, 6, 7, 8. And you see that there's charges on them. So we can predict how they interact with others. These are going to give away 2 electrons, give away 3 electrons, usually going to gain this many electrons. Right. That's just briefly, we'll come back to this more. Okay, so the metalloids are on this staircase. These are the non-metals and the rest are the metals. All right, our exercise now is going to be looking at ptable.com, and you get one of these handouts. Okay, so we're gonna explore, you're gonna go to ptable.com. So the instructions tell you to look at ptable.com. And in this, we're gonna explore some of the trends. Here's one trend, atomic radii. As we go across, they get smaller. As we go down, it gets larger. And you'll see this by going through the left side. There's also a trend on how well an element could grab electrons. Eight main groups. But there's 18 altogether, but the main ones that we don't have the world. Oh, period. Oh, period. Period is 7. Okay, so these are the trends we're gonna explore in this exercise. Okay, we're gonna do this now. Because not only do they follow number of protons and masses, there's these other characteristics that are very important. Okay, use your computer or tablet or mobile device, navigate to ptable.com. It's an interactive periodic table. Everybody there? Okay. And it says, make sure that the Wikipedia tab is selected within this, ptable.com. This will help you explore the elements as we walk through this. And these are just some notes. So this handout is good for notes. Also, that's what we're doing here, exploring. The vertical columns are called groups. How many groups are there? 18. 18 groups. 18 groups. Periods. How many periods? There's 7. Now, this might be confusing, but this slides in here, right? So it happens that these elements have characteristics that should be in here. But that would make this very awkward. It would be very strange to have things way out like that. That's why these are put down here. Using the groups and periods, identify the elements that are located at these positions. Okay. Now it says be in the Wikipedia part, and that's what you're doing now. Okay, so let's keep going on this, fill this in. Okay, so this is an activity we're exploring the periodic table. And then this is to look at trends in the periodic table. How we doing? Any questions? We're gonna wind up drawing some more models.
Do the thing first. No, I literally did it. I literally did it. Hey, what if the three similar problems? Literally, they have the same amount. The same amount of matter. What the What does it say? Literally, it's right there. Literally, you just go.
Guys, we're doing this?
Yeah.
Palladium. And what's this? Group 15. Group 15 is also 5A. Right, we'll talk about the A groups, so those are the ones that we are most confident in predicting their behavior.
Bro, that's on the next. Energy levels. Yeah, it's like energy level. You can say the same thing, it doesn't matter. I don't think anything that energy level is.
And the law of conservation of matter says that the amount of matter stays the same even when it changes form. That's confusing. Can we break it down? You know it. Let's break it down.
Sorry. Thank you.
Rhodium, palladium, silver, lead, and cadmium, and helium, zinc, antimony, then tellurium, and iodine, and neon, and then cesium, and barium is 56, and this is where the table splits. Well, that's of just around. Platinum, cerium, and praseodymium.
We have to learn this before.
Rhodium, medium.
Do I have to memorize the song?
The end of the song is so chaotic.
No, just knowing the end of the song is like it's the most
Thank you guys so much for watching. If you like the song, make sure you check it out on iTunes. And thank you for well. If you make sure you watch the video, like just make sure you top. I'm gonna put some of our videos.
like it doesn't like when. No, it's just statements. I'm not like. Yeah, bro.
Okay. If you're curious, and if you want to waste time looking at YouTube, there are a few posts of little kids that sing this song. I know.
Oh my god, bro. Yeah, you just trying to throw you on. Thank you. I was looking though. That must be wrong. I was following that.
Okay, so this exercise is introducing you to this nice resource with interactive periodic table also, right?
Yes. 15.
It's in Google Classroom to click on when you need it.
What have I done? You know.
Yeah, it is.
I was still. Should we can we turn it on? Do we need is this for homework?
Got stuck on. Right now.
I got a thing. Oh, sure. You can't even read that. You cannot read that. You can't even read that. Dude. Whoa. You no.
Okay.
Yeah, that song is not gonna help you. Like, because it doesn't say, oh, for English, do it.
Okay, so lab books today, please. Take my lab book.
Is it, will this packet be for more? That packet be for more?
This last one.
The thing we just do
No,
that.
I want to see that you got most of it done. That's Monday. The other packet.
Which one?
The atomic structure is due Monday. I'm just getting back some things that I had. See,
That's the only homework we have to do. Just this thing.
yeah, and if you put up with the reading the textbook.
It's been on so many other classes. It is this. Dude. Maybe can be 35 views, like 35 views. Are you watching? Okay. I'm gonna think it's one thing to want it, Jeff, right? I don't know.
Hey, hold on to all these, keep them organized, this is, all these concepts are important.
It literally just needs to be anything that raises to the top. So. If it ends with literally anything other than like. Post transition.